Oh, this is Duncan Foley from Engineering Academy, and today's talk is going to be on Industry 4.0. Just a little bit of a caveat here. Obviously, when you talk about things that are current, very quickly becomes dated. So hopefully you'll find this interesting. We'll have a quick look at the history of factories from 1 to 4.0. What is Factory 4? Look at industry uh, Internet of Things, how we use big data and autonomous manufacturing. So doing a very quick timeline, we can see that Industry 1 can be considered in the 1784 approximately, when mechanization and steam power started. Then came mass production with Henry Ford's car. You can have any Ford as long as it's black. Then we move on to a more automated approach uh, in the sort of 1960s, 70s. And today we're starting to talk about Industry 4 and how everything talks to each other, and how we're getting data in real time, and how we're able to react to that data. So looking at Industry 1.0, the first industrial revolution began at the end of the 18th century. This is generally referred to as industrialization. In this period, the first machines were operated by a power of steam and water instead of human labour. So we had these mechanical looms and things like that. This did have a massive effect on the workforce, with people coming from maybe the farms and stuff to working in this industrialization, and that's where we got our workforce from. But it also meant that the working conditions were much worse when you started working in this area. Then electric motors were invented, and so was the assembly line, which provided the next step in the development. Electricity and motors made it possible to drive the machines independently of water and steam, making them much more flexible. The invention of the assembly line in car production, I think we've all heard of Henry Ford, and provided a significant increase in productivity efficiency at the time of the 20th century. The next revolution was when sort of computers came along, PLCs and stuff. So the transition to the next industrial revolution was made possible by the development of computers, since electronic components were ready for use in industrial environments in the 1970s. Automation had been driven forward in production with electronics, IT, and programmable logical controllers. So we've got an example there of a Siemens PLC. There's obviously lots of different types involved in the Siemens and Allen Bradleys and stuff, but they've revolutionized and allowed us to make improvements to production lines and stuff, and get data far quicker from the production line back up into the office so we can work on it. Digitization, that where everything is talking to each other. So the fourth industrial revolution is now evolving, and with intelligent automation devices and all other systems involved in production being networked in the best possible way. So everything's talking to each other. You know, the marketing are talking to the stores, the ordering in time to get the materials in stock, so that they can go through the factory. We're also looking at how to design the factory, from previous examples I've worked with, where I worked with a company who we worked out that a car brake pad would come into the materials would come into the to make the brake pad would come into stores, and it would literally travel. We worked out 2 miles through the factory before it was completed. So by getting all that data, we could reduce the flow of parts through the factory through discrete event simulation. But also when you start in manufacturing things, maybe on a CNC lathe or a milling machine, and you're getting the data from the coordinate measuring machines, you can see that tolerances are starting to go out. You might need to change a tool bit and stuff. So it's all that, everything talking to each other rather than having islands of automation. But with all that comes an enormous amount of data. And that's where we get to with Internet of Things. Internet of Things, this big data, autonomous manufacturing, digital twinning, which we'll talk about in a bit later, and augmented reality and additive manufacturing. We'll talk about those in a different presentation. Connecting devices to both the internet and other devices to form a vast interconnection of networks is known as the Internet of Things. I suppose an example I could come up with that is I worked with a company who produced aerosol sprays and stuff around the world, and they would own, design, own, and manufacture injection molding machine molds, which were worth up to £250,000, and they would then subcontract them to maybe a foreign country, to maybe Brazil or something, where the mold would go over there and they would be used to produce their products. But it would be a subcontracting sort of thing. We found out that sometimes they were sending these molds out and they were not going to the factory they thought they were. They also felt that some of the production techniques, so the temperatures used and the pressures, were not to recommendations. So what we investigated is putting real-time data coming from the mold from Brazil to Yorkshire in England, and we could see what they were doing with the molds, where the mold was, even, you know, sometimes they send it to a different factory, and how many times it was being used, so we could track it a lot more. So that Internet of Things, that data was really useful for us, so we could work out when the molds, or predict when the molds may fail or start to wear out and stuff. So the biggest challenge is extracting the value from the manufacturing data. So Industrialization, big data comes from many diverse sources, where we're going to get all this information from. So product and or machine design data, such as threshold specifications, machine operation data from control systems, product and process quality data, records of manual operations carried out by staff, manufacturing execution systems, information on manufacturing and operation costs, fault detection. This is great for fault detection, but also helping us collect data where we can predict faults and generate preventative maintenance and stuff before it becomes a problem. So an unusual example of that I came across where I worked on, where we were looking at the large lights used in concerts, and found out that the temperatures would increase just before, and we could predict when the light bulb, these enormous light bulbs, would fail. So we could replace the bulbs before they went out, so you didn't have this problem of the light bulb going out halfway through a concert. Moving on to logistic information, including third-party logistics, customer information on product usage, feedback and stuff. So all this data is coming in, and we need to be able to handle the data but make sense of it as well. So manufacturers today seek to achieve true business intelligence through collecting, analyzing, sharing data across all key functional domains. So it's a matter of getting that data, sharing it where need be, siphoning out what is relevant, what isn't relevant and stuff. And that can be a major problem. There's a lot of university courses designed just to look at collecting, managing, and working out trends from this big data. Moving on, autonomous manufacturing, the increased intelligence of robotic systems allowed for more adaptive systems with varying degrees of automation. A little thing here, when first robots came out and stuff, everybody who could afford a robot would buy them because they were the answer to every problem. And what they found out is unless you've got a reason for having a robot or the next new thing, it might end up being a waste of money. So you've got to, when you're thinking of all these things, think about how it's going to be used, how it's going to be implemented, what the benefits are, and don't be just chasing the next new thing. So machine learning, again, there's an enormous amount of universities who are doing courses on machine learning. It's an extremely complicated world, but it plays a large role in the controlling of robot systems and is responsible for giving the system flexibility. So can it adapt? Is something happening that they need to adapt to and stuff? Rather than, it's just the robot is picking from A, placing it at B, and it's not learning anything, it's not adapting to the surroundings. Also through the implementing of intelligent robots and control systems, it's possible to create dynamic systems responsible for the reconfiguration of a manufacturing system to produce different components to a set of flexible schedule autonomously, drastically reducing changeover periods. Changeover times in industry can be a major problem. That's where you might start wanting to look at lean and agile engineering, something called SMED, which is single minute exchange of dies. This is where you look at how you change from producing the last product A, and then you start the time to producing the next product, part B. Single minute exchange is designing it so you can change over as quickly as possible. A quick example of that would be a Formula One racing car when it comes into the pits to get all four tyres done. If we would change our four tyres on our car, it would take us ages, where they're managing to do it in 2.4 seconds, which interestingly, it takes you longer to say 2.4 seconds than 2.4 seconds. Autonomous manufacturing, the most important things for this is to identify and save production data. What data do you need? Can you collect it? How are you going to collect it? At what time frames are you going to collect it? Do you need it every second, or do you need to collect the data at the end of a shift or every hour and stuff? And you need to improve the quality system. Improve quality. It's important to ensure that the details of the defects are recorded. So if something's going through production and there's a problem with it, why is the problem? What is the problem? Can you get back to where it was originally made and solve the problem? 4 steps to developing the foundations for Industry 4. Establish data science capabilities in-house or by partnership. So who's going to collect this data? I know a lot of big companies actually subcontract that out, and I know one company in Manchester, England. The data is collected 30 miles away. They collect the data, they put it into some sort of presentable format, and then send it back to the company in real time. You need to build a system capable of aggregating business information from multiple data sources. So you're going to get all this data from, enterprise resource planning, the warehouse, and it's all going to come in, and you need to have a system that's capable of handling all that. Audit the warehouse devices to determine where Internet of Things data can be harnessed to augment and enhance business data. So warehouses are a great place to start looking at Internet of Things. Going back to the music industry, I know that a lot of them, they put RFID chips in there to know where things are. And another example would be Walt Disney World. They spent an enormous amount of money on RFID chips. I think it was $1 billion, where every person who goes through the park who's got a band on the wrist to scan to get into the park, everything's known about where they are in the park, where they're going, what they're buying, are they going on a ride, are they getting a picture on the ride? can Walt Disney sell them that picture afterwards? And all that mass, imagine the amount of people going into Walt Disney World and they're getting this data in real time, you know, the routes they're going through the park and stuff. It needs to be able to be handled, tracked, and then analyzed and made sense of, basically. And sure, the collected data can be interpreted. That's what I'm saying. You know, if you can't, if you've getting all this data, but you don't know how to make sense of it, then it's pointless. It's very hard to see that, but if anybody needs any of the references, feel free to email me. I did do quite a lot of research there, and I've used a lot of links and stuff. But you know, you're more than capable of using Google or Google Scholar, um, or your own research papers and stuff that you can search yourself, or a library. Hopefully that was been useful to you. If you think it has, then please subscribe to Engineering Academy. If you've got any questions, then great. Email us at engineeringacademylearning@gmail. Have you looked at anything we've done, or you know, does this presentation today inspire you, or you've done something on Internet of Things? You think, you know, I could add to what we're saying here, and show us what you've been doing at your own company. And it'd be really great to, you know, see what you're doing. So contact us and maybe get a recording done so you can add to this collection of videos. Let us know if you would like to cover some topics yourself in sort of general field of engineering. Just email us, and we'll try and get you up and on. Excellent. So that was Duncan Foley from Engineering Academy. I hope this was useful to you guys. Thank you.